Hello everyone, again welcome back to the latest lecture session. We were discussing some parameters with respect to water quality or wastewater quality, I guess, right? And we were discussing, I believe, organics or indirectly estimating organic content in the water by looking at BOD and COD. Again, we looked at why, I guess, we would prefer rather every citizen to be aware of these water quality parameters, right? Again, we want you to be knowledgeable to take decisions and also obviously to prevent pollution at a personal level, let's say, or at an individual level, right? So in that context, we were looking at oxygen demand, right? Or not or, as self-explanatory. We are talking about oxygen demand of a particular compound, or in this case of water, let's say, or all the organics in the water, right? And two ways to measure them usually. One is biochemical oxygen demand, which measures the amount of biodegradable organic content or biodegradable content in the water, right? Again, which can be oxidized to CO2 and H2O by microorganisms. And COD, obviously we were looking at oxidizing the relevant water or the organics by a strong oxidizing agent. So how do we go about measuring BOD now? Well, like as I mentioned, it's pretty simple. So we are looking at the oxygen demand, right? So you take the sample from the river, let's say, right? Yes, you can measure the initial dissolved oxygen. You can do it by titration, or you can use a DO probe, right, and get the dissolved oxygen. So here looks like the initial dissolved oxygen for this sample is 2.58 milligram per liter, right. So that's one aspect. And then moving on, what do we have? So after a certain period of time, I can get the dissolved oxygen, right, and then let's say it's 4, let's say 4 milligrams per liter is the dissolved oxygen, 4 milligrams of oxygen per liter of water. So the difference will give me the oxygen demand, let's say, right, oxygen demand during that period. So typically we look at BOD 5 days or BOD or oxygen demand over 5 days. Why 5? I mean, when I guess some trivia, let's say this is UK, let's say, and I think the scientists that were looking at it way back, I guess, noticed that it took 5 days for any of their rivers to reach the relevant shore, let's say, or the ocean now. So they were looking at the oxygen demand within that particular period. That's what I believe I read in a book about, or with trivia. So in general, that's one of the reasons that can be plausible. The other reason is that most of the carbonaceous oxygen demand will be consumed within 5 days. That's another aspect. So I leave it to you to dig up and see which one is the right reason for choosing 5 days, right? So let's move on. Let's look at what we have here. So you are going to take the sample on 0 day, right, and a sample on 3 days or after 5 days, right. For this one, you will measure the DO immediately, or the dissolved oxygen, let us say 8.58, which is what we are doing out here. So this one you will put it in an incubator, right. Why are you closing it up? Because you do not want photosynthesis to occur, that is why you are closing it up, so that there is no light, access to light. And we fill it to the brim because you do not want any oxygen trapped in this air bubbles to go into the water and lead to under or overestimation of your relevant or underestimation of the organics here, right. You want to prevent that. So you are going to fill it to the brim, put it in here, and obviously as we just discussed, you are going to put it in there for a standard period of time. Typically it is 5 days at a temperature of 20 degrees centigrade. You can set the temperature here in an incubator, or for 3 days at 27 degrees centigrade if you are short of time, let us say. But if you look at the rate constant and the change with respect to temperature, more or less both the values approximated by this combination of time and rate constant will be relatively similar. So, right, you are going to take the difference in oxygen demand, not oxygen demand, dissolved oxygen at the 0 day and the X day, which is either 3 or 5 days, right. So again, a better example, or not better example, hopefully a more detailed explanation can be available or will be available at this link, let us say, right. So let us move on and then measure the DO. I think we are done with this. Let us move on. What is this now? BOD test employs a bacterial seed, okay. So, typically the waste waters that you collect out there are going to have some bacteria, let us say if it is from sewage treatment plant and such, your feces are going to have bacteria or such, right, and that is good enough, you do not need to add bacteria. But let us say if it is an industrial wastewater sample in which you have no bacteria present to kickstart the microbial process. So, what do you need? You obviously need to add bacteria, let us say, which is called bacterial seed here. And in such cases you will also need to add some nutrients, nitrogen, phosphorus and so on, but that depends on the kind of water. So, again what do we have here? The BOD test employs a bacterial seed to catalyze, right. Again I think we mentioned this earlier, we have a reduced form of a compound and it can be oxidized to CO2 and H2O. So, what is the role of the bacteria here? Typically this can occur, but the kinetics is way too slow, right. So, the bacteria are going to catalyze this reaction, how? By releasing the enzymes, let us say, which are going to lead to faster kinetics. But why though? Why would they want to do that? Well, because they want to thrive, they want to duplicate or multiply, I guess, right. Similar to humans, they want to eat and get the energy. So, from this reaction the energy that is given out will be used by them for their metabolic process or for multiplication, and also the nutrients too, some of it will be consumed along with some carbon for the cell synthesis, I guess. So, that is why the bacteria want to do that. Anyway, that is enough technical content here for this generic class. And what do we have? Oxidation of 300 ml of full strength or diluted water, we will look at that. And then I guess the strength of the undiluted wastewater is determined from the dilution factor and so on. Well, blah blah, we typically do not encourage formulas and mugging up. Let me just try to look at an example if I have it here and then explain it in a better manner. So, what do I have? I want if I want to calculate the BOD at time t, which is 3 days or 5 days, what do? I take the dissolved oxygen on the 0th day initial and the dissolved oxygen on the 3rd day or the 5th day, which is the final, let us say, right, initial and final. So, the difference will give me the oxygen demand, right, oxygen demand, because the compounds are being broken down by microorganisms. Obviously, we are talking about biochemical oxygen demand, right. Typically, it is the biodegradable fraction of the organic matter that can be aerobically degraded, right, aerobically, because it is in the presence of, we are talking about in the presence of oxygen. I think we have a figure here before we move on to an example out here, right. So, we have oxygen demand on the y axis and on the x axis we have time, right. And here what is it now? We see that initially there will be a lag phase, but that is not typically or visible out here. So, after the lag phase there is going to be an exponential demand, or the demand for oxygen will see exponential increase. And what do we see here? When a sufficient number of nitrifying organisms are present, nitrification can occur as shown by the dotted line. Okay. So, I understand what it is that we are trying to say. So, in the water you are going to have, let us say, carbonaceous organic matter and also let us say ammonia, let us say, right. Even ammonia can be oxidized to what now? Let us say NO3 minus or NO2 minus, right. So, for this also you are going to need some oxygen demand. So, ammonia or such or reduced forms of nitrogen can also exert some oxygen demand, which is why you will typically try to prevent that, and that is why you will add denitrifiers. Okay, I have that written out here. So, nitrification inhibitors will be added, or not denitrifiers, I guess the right term is nitrification inhibitors will be added to prevent this particular set of reactions where ammonia will be oxidized to NO3 minus or NO2 minus, right. We are typically trying to calculate the carbonaceous oxygen demand, right. So, and in general though, in nature, while this organic matter or the carbonaceous organic matter is being degraded, typically the nitrogenous biochemical oxygen demand will not exert itself, because the bacteria which thrive or which like feeding on this nitrogenous biochemical oxygen demand will not thrive when you have carbonaceous organics, let us say, right. So, that is one reason, but if you have a different type of wastewater, sometimes you will have these nitrifiers or such. So, that is why you will have nitrification inhibitors out here. Again that is enough, but what do you see in general after 5 days or 8 days you are going to see this profile, and typically 5 days will be somewhere out here, right. So, initial oxygen demand and final oxygen demand, I guess, again oxygen demand, pardon me, this is not oxygen here. So, right, that will give you the oxygen demand. So, obviously as you see, as we spend more time, the microbes are consuming the organic matter and the oxygen, or degrading the carbonic matter and the, not carbonic matter, pardon me, the organic matter and the oxygen, right, and that is why you are seeing it, the demand for oxygen increasing, right, and after some time you will have no more carbonaceous organic matter, and you will now see the nitrogenous biochemical oxygen demand coming into play, right. So, that is something to keep in mind, but I think I have a better figure out here. Again, just couple of simple examples to illustrate the relevant aspects. So, we have initial, if the initial DO of this sample, let us say, is 8 milligram per liter, and the final DO after 5 days is 2 milligrams per liter, what is the BOD of the sample now, right. So, again this is pretty much simple, I guess, right, BOD of the sample, and this is after 5 days. So, we are going to call that BOD 5 is going to be equal to the difference in the oxygen, what do we say, dissolved oxygen that was measured before and after incubation. So, 8 minus 2, so that is going to be equal to 6 milligram per liter, right. So, well, that is pretty straightforward, but in general, as we have seen from some of the other or previous slides, we typically do not come across such low values. For example, I think for Yamuna we saw that the BOD was 30 to 40 milligram per liter, river Yamuna, let us say, right, and this poses some challenges with respect to measurement. And also, for example, I guess typical sewage BOD, sewage meaning we are feces and urine and so on and so forth, will be around 200 milligram per liter, but obviously this feces and what this urine and such will be diluted by your waste water from kitchens and bathrooms and so on, right. So, that is something to keep in mind, but one aspect is that the BOD values that you typically come across are much higher than this pretty small values. So, we have another example out here, right, that will illustrate the aspect that we were discussing earlier, as in if my BOD is high, what are the issues or such, and how can I measure the relevant sample. So, here we have a sample with initial DO of 8 milligram per liter, and after 5 days 0 milligram per liter. So, here BOD 5, I guess what is it equal to? Well, the simplistic calculation would be 8 minus 0. So, that is equal to 8 milligram per liter, right. But here obviously, as people would have noticed, that can't be true, because here this case is that you have considerable organic matter that can be biodegraded aerobically, and you have oxygen, some oxygen, limited oxygen, right. Why do we have limited oxygen? Because the Henry's constant for oxygen, let us say, right, and at the relevant temperature and pressure, the maximum I think around 25 or 27 degrees centigrade, the maximum dissolved oxygen is around 9 milligram per liter, right. So, water can't hold more than 9 milligram per liter. But that organic content, relevant equivalents, let us say, can be relatively higher obviously than 9 milligram per liter. But let us say we have high organic content and let us say only 8 milligram per liter. So, we do not know whether this dissolved oxygen level of 0 has been achieved, let us say within the first day or right at the point you are taking the sample out and measuring the DO, right. So, you do not know that. So, obviously, when your dissolved oxygen, the final dissolved oxygen is 0, you can't make a BOD or organic content approximation, let us say, right. So, what do you need to do? You need to obviously see to it that your dissolved oxygen is not too low. When I say too low, obviously I need some value. So, what is the threshold I am looking at? Let us say if it is 0.1, am I fine? Well, not really, because let us say at 0.1 or even below 2 milligrams per liter of dissolved oxygen, 2 milligrams per liter, please note the threshold, lower threshold. Your microorganisms are not going to thrive or multiply as they usually do at higher dissolved levels of dissolved oxygen. So, if the final DO is less than 2 milligrams per liter, you are not going to consider that particular measurement, right. So, you need to see to it that your final measurement is less than 2 milligram per liter, right. So, how do I go about that? Obviously, I am going to have to dilute the sample, right. So, that is why we are going to say that, let us say I have high organic content, let us say x milligram per liter, and let us say I estimate it to be around 800 milligram per liter or 200, let us say 800, and I know that the change has to be around, let us say 8 minus 2. So, the change can be a maximum of 6, right. So, accordingly I can dilute it here, let us say, right. So, 6 milligram per liter is the maximum oxygen demand I can measure practically, let us see, right. So, I have to dilute it by a factor, let us say 100 or more than slightly more than 100, such that the difference between final and initial will be what is it now 6 milligram per liter, right, or less than 6 milligram per liter. So, let us look at the example that I have. So, as we just mentioned or discussed out here, so if DO is less than 2 milligram per liter, reliable measurement cannot be made. Why is that? Because the growth of the microorganisms is going to be affected, right. Again, pretty simple stuff, so we are not going to go through that. So, as I mentioned, what are we going to do? We are going to add the seed bacteria as discussed. For some samples you do not have bacteria present, so you need to add the bacterial seed, and similar to us, the bacteria need nutrients to thrive. So, that is why you are going to add some nutrients. So, typically we call this to be the seed 2, just a second. So, we call this to be the seed, right, and then to make sure that the water you are using, which is called the seeded dilution water, has high enough initial dissolved oxygen, you are going to aerate it, right, such that it is almost at the what is it now, equilibrium or at equilibrium with the oxygen in the atmosphere, right. Henry's constant, I think we talked about this, right, concentration in the gaseous phase to the concentration in the aqueous phase, right. So, we aerate it long enough so that it is at equilibrium, and then you are going to use that what do we say, or measure the organic content if any in the dilution water also by sealing this initial and final, and then you will use this what do we say, aerated seeded dilution water to dilute your sample. For example, let us say earlier we talked about initial or not the initial, the organic content of the sample being around 800 milligram per liter of oxygen equivalents, right. So, let us say that, let us say you want to dilute it by what is it, 100 times, let us say, right, 100 times, right. So, what do you need to do? You will take 3 ml of the sample, right, and you will fill it up to with 297 ml of your what is this, seeded dilution water. So, what are you doing it? Here you are diluting it by 100 times, let us see, right, 3 by 300, you are diluting it by 100 times, right. So, that is what we have out here, and you will conduct your BOD test on this particular sample now, right. So, that the change in oxygen, what do we say, dissolved oxygen before and after, or DO initial minus DO final, the change let us say is less than 6 or around 6, let us say, right. So, that is what you want to try to do, right. Again, why are we also conducting the BOD test on this dilution water? Because depending on where you got the water from, there might be some organic content in this water too. So, you will also conduct the BOD test on this water. So, how do you measure the BOD, or how do you get this particular BOD of the sample, which is the one in this 3 milligram per liter, right. So, I guess it is mass balance. Again, people talk about this what is this formula and so on and so forth. I am not one for mugging up formulae. So, let us move on and look at the mass balance, I guess, right. Again, simpler stuff, I think I already covered this. So, it is not worth going to into these aspects again, right. Let me move on. So, again fundamental approach, again mass balance. So, it is that before and after dilution you are still going to have the same organic content. For example, in here I have my sample and here I have my dilution water, let us see, right. So, this I am going to call the mixture. So, the total organic content in the mixture will be equal to the organic content in the dilution water plus the organic content in the sample, right. So, that is what I have out here, right, sample dilution water. So, how do I get this in terms of the variables that I have? So, it is going to be nothing but the volume of the mixture, right, volume of the mixture into BOD of the mixture, right. BOD is what, let us say 8 milligram per liter, let us say, right, and volume cancel out, and then you are going to get in equivalent terms the organic content that is present in the mixture. So, volume into BOD will give you the organic content equivalents will be equal to volume of the sample into BOD of the sample plus volume of the dilution water that was used into BOD of the dilution water, right. So, what are you measuring here in your experiment? You are measuring this BOD of the mixture and also BOD of the dilution water, and you know the other values, as in you know how much sample you are taking 3 ml in the previous example and how much dilution water you are taking, which is 297 ml. Volume of the mixture is volume of the sample plus volume of dilution water, which is typically 300 ml, right. So, you have all the other unknowns, so you can calculate the BOD of the sample, right. So, that is what we have out here. Again, this is the fundamental approach, and I would always suggest that we look at this fundamental approach. And obviously, if what is it now, sometimes you have no organic content detected in your what do we say this dilution water, then obviously this term is going to be 0, right. So, that is what we have out here. So, let us look at an example out here. Okay. So, we have a test from what do we say river Yamuna, the wastewater being conducted, the wastewater going into river Yamuna rather, and the BOD test is run by adding 3 ml to 300 ml. So, what is this 3 ml? 3 ml is the volume of your sample is equal to 3 ml, and volume, and we make this up to 300 ml. The total volume of mixture, pardon me, is equal to 300 ml, right. And so, from this obviously volume of your dilution water is equal to 297 ml, right. And if the bottles are filled to capacity with seeded water, not if, the bottles are filled to capacity with seeded dilution water, initial DO of the mixture. So, right, DO initial of the mixture is equal to 8 milligram per liter, and the DO final of the mixture is, and which is after 5 days, is 2 milligram per liter. I guess I chose it conveniently. And so, what is the BOD of the wastewater, right, or of the sample? The sample is the wastewater. Assume that the seeded dilution water has negligible oxygen demand. So, what does this mean? This means that the BOD of your dilution water is equal to 0, right. So, what do we have, what did we look at earlier? Our mass balance, volume of the mixture into BOD of the mixture is equal to volume of the sample into BOD of the sample plus volume of the dilution water into BOD of the dilution water, right. But here we see that it has negligible oxygen demand. What is it? The seeded dilution water. So, this term goes to 0, and volume of the mixture we know it to be 300 ml, and we know that the BOD of mixture is nothing but 8 minus 2, which is equal to 6, is equal to volume of the sample. Volume of the sample is out here 3 ml, pardon me, into BOD of the sample, which is what we want to calculate. Therefore, the BOD of your wastewater or the sample is going to be equal to, I guess, 600 milligram per liter, oxygen equivalents obviously, unless I messed up some calculation here, right. So, let us see out what we have. Well, I guess plugging into formula, but again I do not like this. So, here we have 600 milligram per liter, right. So, moving on, COD, as I mentioned, we do that because it is relatively fast, 2-hour test, but obviously it is expensive. Each test I think is around 400 rupees or such, which is obviously pretty costly compared to the BOD test, right. So, COD, how do we measure that? Again, it is chemical oxygen demand. So, we are going to add a strong oxidizing agent, which is in this case dichromate, right, Cr2O7 2 minus, or here I guess we are talking about potassium dichromate. Here I think oxidation state is 7 2 is 14 minus 2, let us say 12 2, so plus 6, and I think it will go to plus 3, let us see, right. It is going to oxidize something, right, it is going to accept electrons, and chromium is going to change from oxidation state plus 6 to plus 3. Again, we conduct this test in 2 hours, right, in the presence of acid and in the presence of silver catalyst, right, and we typically also add mercury to rule out the effects of Cl minus, but again this is way too much technical content for this class. We are not going to look at that. So, obviously, the COD it is measured by using a strong oxidizing agent. So, it is going to measure both organics, inorganics, or both the biodegradable and non-biodegradable matter too, I guess, right. I should not say organics and inorganics, I should say both the biodegradable matter and non-biodegradable matter. So, it will typically always be higher than BOD, let us see, right. Again, one distinction is that looks like we will not be what do we say, measuring the oxygen demand due to the nitrogenous species, right. So, that is something to keep in mind. So, again just what we discussed earlier. So, thus COD will always be greater than or equal to BOD, right, because this is biodegradable and non-biodegradable, this is only biodegradable, right. We are looking at what the microbes can degrade here with respect to BOD. Theoretical oxygen demand, well, I guess this is going a bit overboard, so I will skip those aspects. So, total organic carbon, again different instruments, let us say, to measure the amount of organic carbon. This, I guess in a few minutes you will get that. This is also another indicator of organic carbon, but I will not bore you to death because I do not feel that this level of information is necessary. Okay. So, for example, I mean typical pretty simple straightforward exam questions to keep you interested again, obviously. If 1 milligram per liter of glucose is completely oxidized to CO2 or mineralized, let us say, I guess just to CO2 is not going to be feasible. Find the theoretical oxygen demand, chemical oxygen demand, BOD, BOD 5, let us say, and total organic carbon. So, let us see how we go about it. Theoretical oxygen demand, it is just the formula out there, right. So, what do we have out here? This, we are going to have to balance, right, CO2 and H2O, but if N is there, okay, I say glucose, okay, I see what I did. So, here the question was for glucose, but again here I see that I asked another question about what is this glutaramide. So, because we have the solution for glutaramide, we are going to work it out for that, let us see, right. So, again let us see what we have here. Here we have N2, right. So, that changes the relevant scenario out here. So, again as we mentioned earlier, theoretical oxygen demand COD and BOD, we assume that the end product is NH3 and this is not going to be further oxidized to NO3 minus or nitrite, right. Again what do we have here? We balance the equation out, let us say you have 1 milligram per liter or how much glutaramide, I guess we are assuming it is going to be 1. Anyway, theoretical oxygen demand, it is going to be, I guess, equal to the molecular weight 10 into 16, 160, right, and here I guess it is 113. So, you are going to need 1.42 milligrams of O2, right, per what is that 1 milligram of glutaramide, right. So, that is one thing out there, theoretical oxygen demand. And chemical oxygen demand, it is going to be equal to 1.42 or similar, I guess, right, because here you see for the COD and BOD is the same, not BOD, theoretical oxygen demand is the same. So, it is 1.42 milligrams of O2 per milligram of C5H7NO2, let us see, right. So, for example, if it was 1 milligram per liter of glutaramide, then you can multiply or divide accordingly, I guess, and then multiply, I guess, right. We know that it is 1.42 milligrams of O2 per milligram of the C5H7NO2, and if I know that it is if the glutaramide concentration in water is 1 milligram per liter, 1 milligram per liter. So, I guess it is going to cancel out and my BOD or here I guess the COD is going to be equal to 1.42 milligrams per liter, right. Again that is a pretty simple aspect. So, here BOD, I guess here we are talking about ultimate meaning if we let the test run for an infinite amount of time. So, assuming that this is completely biodegradable, BOD ultimate will then be chemical oxygen demand, right. So, that is something to understand. and then we were asked to calculate BOD 5 approximation. So, here you are going to use a rate constant, and if you look at the time, you will see that typically BOD 5 days is equal to 68% or typically 70% of BOD ultimate, but I will typically not ask questions like these, right. You are going to have 0.68 into 1.42, so 0.97 milligram of BOD 5 per milligram of C5H7NO2. So, total organic carbon obviously 5, right, 5 into 112, not 112, pardon me, 12, right, molecular weight per 113 what do we say, grams of C5H7NO2. So, 0.53 total organic carbon per milligram of C5H7NO2, right. So, that is something to keep in mind, just petty calculations to get your juices flowing, I guess. So, estimating BOD, let us see. Okay. So, this is the key aspect here, and I guess since I am almost out of time, I will end my class here, but in the next session we are going to look at estimating the BOD, or for that case we obviously need to understand how to estimate systems, let us say. All right. For example, I have a river, let us say, or a lake, and I want to estimate the BOD of that particular lake, given that I know that the BOD coming into the lake from a waste stream is, let us say, 50 milligram per liter. How do I estimate the BOD of that lake? What are the long term implications and so on, right. So, I guess I am out of time. We will look at this in the next session, and thank you for your patience as usual.